All right. In this particular part of the unit, we are going to look at Euler paths and circuits. And I know that that name looks like it should be pronounced Euler, but it is pronounced Euler. A route around a graph that visits every edge once is what is called an Euler path. Okay? Every edge, Euler path. The way I remember that Euler means is about edges is Euler starts with E, every edge starts with E. Okay, so a path goes around every edge one time. That is an Euler path. Okay, the difference between just a regular old path, like we talked about in the last page of the notes, and an Euler path is that a regular path does not have to go through every edge on a graph, but an Euler path does pass through every edge exactly once. Okay, and a path can begin and end at different vertices. Okay, it doesn't have to, but it certainly can. Now, an Euler circuit is a circuit that passes through every edge of the graph exactly once. Okay, remember a circuit is a path that starts and finishes at the same vertex. So every Euler circuit is also an Euler path. The difference between the circuit and the path is that a circuit must begin and end at the same vertex. Okay, so Euler, anytime you see Euler, that means every edge. Okay, an Euler path means I have to go on every single edge. It doesn't matter if you start in the same spot that you finish. And an Euler circuit means you begin and end at the same spot, traveling every edge along the way. All right, so we are going to take some of these graphs here and these examples, and we are going to see if we can find an Euler path and or an Euler circuit for each of the graphs. Okay, if it's not possible, we want to try to explain in the best way that we can why we don't think that that's going to work. All right, so for this first one here, looking for an Euler path, that simply means we need to travel every single edge exactly once. All right, so I'm going to start at vertex A just because it seems like a decent spot to start, and we may have to kind of begin and backtrack a couple times, and that's pretty natural. And what I'm going to do is I'm going to trace along the edges as I go, because again, the goal is to use every edge exactly once. So I'm going to go from, let's say, A to vertex C. Okay, and I have to go around every edge. So I'm going to go over here to B next, and then to E because I don't have a choice. And then I'm going to go back to C, and remember it's okay to go through vertices more than once. I just can't go on an edge more than one time. So from C, I must have to go to F. From F, I clearly have to go to G. From G, I have to go to D. I have no idea why I started drawing arrows there instead of just little dashes. I think I just translated that from my graph on over. And then from D, I end up back at A. Okay. Now, if I need an Euler circuit, and I'm only using an E there, by the way, E path and E circuit to represent Euler, so we don't have to write it out every single time. An Euler circuit, actually, it's the same thing as above. What's right up there? Because remember, a circuit means that you start and end at the same vertex, and we did. Okay, we did start and end at the same vertex. So when I found a path, I happened to find the Euler circuit at the same time. And occasionally that happens. You kind of get like 2 for the price of 1. All right, for this next one here, finding an Euler path. So is there a way to start somewhere and travel every edge exactly once? Okay, so one of the most common things to do, I'm going to start at vertex A. So if I start at vertex A and I start traveling on these edges, once I get to E, I have a problem. If I go on to B, I can't get back here and use the edge DE. That's a problem. And once I get to E, if I decide, okay, well, I'm going to go to D instead, then I still can't use this edge from E to B. So starting at vertex A is clearly not the right solution. So what if I start at D? Well, if I start at D and go to A, I'm already going to be stuck because I can't leave vertex A. If I start at D and I work my way around the triangle, again, I'm stuck. I don't have a way to get back to B and E. And I think you'll find if you play this with this one enough, you can't do it. There is no Euler path. Okay, this is going to be not possible. Okay, and usually it's because like there's no way to get in and out of either A or B. Those are usually the ones that are kind of the problem children. Like once you get somewhere, there's either A or B that you just can't get to. Like you're stuck. You can't get to every single edge. And so it's kind of hard to put that into words at sometimes, but I'm going to do it this way. So I'm going to say like vertex B is a problem. I can exit, but not enter. So like I can leave vertex B, but I can't get back. Or I can enter and not exit. There's like there's not a way to make that happen. Like I'm stuck. There's always an edge that it turns out that we're missing. We kind of get we get trapped essentially. Okay. In Euler's circuit, we're going to run into the exact same dilemma that we just ran into. An Euler circuit, remember, has to begin and end at the same vertex. Well, if I can't, and use every edge. If I can't use every edge not beginning and ending at the same vertex, I'm certainly not going to be able to begin and end at the same vertex and use every edge. So again, not possible, and I'm just going to put C above. It's kind of the same reason. I get trapped at some point. All right, moving on to this third graph. So an Euler path, I'm just going to, again, kind of randomly pick a spot to start. I'm going to pick vertex A as my starting spot, and we're going to travel along the edges as we go. So from A, I can go to, and again, kind of pick, let's just go to E. From E, I don't have a choice. I have to go to F. From F, you got all kinds of choices as to what you do. I'm going to go to G. I'm going to keep moving around. I'm going to go to H next. Then I'm going to go up to D and over to C. Then I'm going to go ahead and go over to B. And I have to travel every edge. So I don't want to go back to A because then I'd be trapped. But from B, I could go back to vertex F. And then I have to go to C. And then I would have to go to G because that's the only edge I haven't traveled. And then I have to go to B. And then last but not least, I find my way back to vertex A. So there is an Euler path. Okay. An Euler circuit, guess what? We have one. We started and ended at the same vertex, vertex A. So that is our Euler path. We don't have to, or our Euler circuit and our Euler path. We don't have to come up with another one. Those happened to be the same thing. Okay, so this next one here, let's try again an Euler path. So if I was going to start like at vertex A, which is kind of where I typically try to start things, if I go from A to E, then I don't know, let's go over to D, then I could go up to B, then I could go back down to E, then I'd have to go over to F. I wouldn't have a choice. I don't want to go back to A because if I do, I haven't used two edges, so that's going to be a problem. So I guess I have to go up to C, and then I can go up to B, and then, okay, we have an edge we haven't used. We haven't used A to F, so that may not be my best option. So I'm going to go and I'm going to erase. We're going to try again. Let's try instead starting at vertex B, see if anything goes any different, because you never know. Sometimes it takes more than 1 or 2 or 3 shots at this. So let's start at vertex B. Let's say we travel across to vertex C, and then we'd have to go to F. From F, we do have a choice. So I'm going to go ahead and go over to A and then down to E. From E, now again, my only rule is here, I want to travel everything at least once. So I don't want to go over to F. That would be bad. So from E, I'm going to go ahead and go up to B. Then I'm going to go down to D, then over to E, and then over to F. And so we have found an Euler path. There's one, and you may have found a different one. For an Euler circuit, we're going to have to begin and end at the same vertex. Begin and end at the same vertex. So we know we can't start at A. There wasn't even a path. So let's try from B. That might be a good idea to get a circuit in there. So is there a way to kind of begin and end at, say, vertex B? Okay, so let's start out at vertex B, and I'm just going to do a little tracing here. So I could go from B to D to E, maybe to A to F, and then I think you're going to see what the problem is here. Okay, if I go to C and I go to B, right, if I go this way and then to B, I'm back at B, and then I leave B and there's no way to get back to where I started. Okay, that's kind of the whole problem, is I can't get back to where I started. We already tried it with vertex A. We didn't even find a path out of vertex A. I think with C, we would sort of find the same thing is going to happen if you start tracing what's going to go on. If you start at vertex C and you have to get back to where you came from, again, at some point we get here and we got to go to C. If I go directly to C, I have two edges I haven't used. If I wrap back to E and then to B, I still haven't used an edge and I can't go back to C. So we kind of get stuck. Okay, those vertices with odd degree are a problem. Because once we go in, we can go in and we can go out, and then we go back in, and then we're stuck. We can't get back out. There's not another way to get out. And so in that case, we'll find that this particular graph does not have an Euler circuit at all.